Today we are going to discuss formulation of tablets. As we know that the tablet is a ruling dosage form. We are not at present discussing the classification. We are focusing on the formulation first. So formulation is nothing but the list of ingredients. So this is the list of ingredients which are normally present in a tablet. It contains API, that is active pharmaceutical ingredient, diluents, that are also known as fillers, binders, disintegrants, gradient, lubricant, and antiadherent, and miscellaneous agents. The miscellaneous agents include coloring agents, sweeteners, though they are rarely used, anti-capping agents, etc. First is API, active pharmaceutical ingredient. All the tablets except the placebo tablets, they contain active pharmaceutical ingredients and their quantity is fixed by regulations. So, the only API that are absorbed through GIT, which can be ingested through oral route, they are included in the tablet formulations. There are a number of examples for which tablets are not available. The most classic example is of that of insulin. It is a peptide and it is digested in GIT, and that is why it is not administered through oral route. Though research is going on to administer insulin through oral route, but till date there is no solid solution available for that. Now, diluents, fillers or bulking agents. Diluents are the major part of the tablets. The diluents are present in a tablet to increase the bulk. Now, there are mainly two purposes of including the diluents. First one is they are incorporated to increase the bulk. When your active ingredient is having dose less than 50 milligrams, normally the tablets which are having weight of less than 50 milligrams, they are difficult to handle. And that is why to increase the bulk, we are incorporating diluents. Second purpose is to increase the compressibility and flowability. There are a number of API for which dose is more than 50 milligrams, but they are poorly compressible. And hence, in order to enhance their compressibility and flowability, we incorporate the diluents. The examples of commonly used diluents are lactose, mannitol, microcrystalline cellulose, dicalcium phosphate, diabetic calcium phosphate, modified starch, etc. Lactose. Lactose, as we know, is a milk sugar. It is obtained from milk. Lactose is available in two different forms. One is crystalline form and another is spray dried form. Most commonly in the industry at present, we are using spray dried lactose owing to number of advantages. Because of spray drying, the lactose is having spherical shape. As it is produced from droplets, its shape is nearly spherical. At the same time, it is porous because during spray drying, the solvent molecules from the center, from the core, will evaporate, leaving behind the pores, and that makes the lactose porous. This imparts two important properties in lactose. Because of sphericity, it is having better flow. And because of porosity, it is having better compressibility. That are two essential attributes which are required in order to become a directly compressible excipient. So, spray dried lactose is a directly compressible excipient. It is GRAS listed, that is generally regarded as safe. It is also included in IIG, that is inactive ingredient guide of US FDA. It is available under the brand names like Spherolec, Flotec, Fast Flow, Supertab, etc. Sometimes in your exams also, particularly MCQ type exams, they are asking the brand names. This contains what ingredient? So there are few brand names. Spherolec. The name is spherical lactose. Flolec. Lactose which is having good flow. Fast flow. Super tab, etc. It is incompatible with the drugs which are containing primary and secondary amines. It shows a delayed kind of reaction that is known as Maillard reaction. In this reaction, the tablets will change its color from yellowish brown, from white to yellowish brown, and that's a delayed kind of reaction. So sometimes it can be asked in an exam with a particular drug, which diluent should not be used. So you need to know the structure of that. If it is containing primary or secondary amine, we cannot use lactose because it is giving Maillard reaction. It's a delayed kind of reaction. On storing the tablets for 6 months to 1 year, the color will change. And that's why we need to take care of that. Next is microcrystalline cellulose. It's a semi-synthetic derivative of cellulose. Cellulose is obtained from plants, and By modifying this cellulose, we can produce microcrystalline cellulose. The commonly available brand name of microcrystalline cellulose is Avicel. Originally, it was marketed by FMC Corporation. At present in India, it is marketed by Sigma Aldrich. This Avicel or microcrystalline cellulose is available under different grades. Now, lactose is water soluble, hygroscopic, while MCC is hygroscopic but water insoluble. It is not soluble in water, but it is hygroscopic. It can absorb water. The main problem with the lactose is spread dried lactose, particularly is on storage or in presence of high amount of moisture, it can crystallize and it can convert to crystalline form. Spread dried lactose is amorphous form. It can convert to crystalline form, while MCC is not having such an issue. So it can be used for direct compression as well. It is having good flow, good compressibility, and that is why it can be used for direct compression. It is hygroscopic, hydrophilic, and water insoluble. Other brand names of MCC are Celfier, Pharmacell, Tabulose, etc. And it is incompatible with strong oxidizing agents. As it is cellulose, it is obtained from plant and it can burn. So, in presence of strong oxidizing agents, it can catch fire as well. But normally in tablets, we are not incorporating strong oxidizing agent, but still it is incompatible with them. Now, these are the different grades available for Avicel. Avicel pH 101. The grade pH indicates pharmaceutical grade. pH indicates pharmaceutical grade. 101 is a grade which contains, which is having nominal particle size, mean particle size of 50 microns, and moisture content is less than 1%. Okay, moisture content is less than 5%. Avicel pH 102 is having the nominal particle size of 100 microns. So it is somewhat coarser grade. When we want to go for direct compression, we prefer larger particles. When we go for granulation, we will prefer Avicel pH 102. If we go for direct compression, we will prefer Avicel pH 102 in presence of 101. It is having less moisture, less than 5% moisture content. Similarly, Avicel pH 103 having particle size of 50, but moisture content is less than 3%. So if your drug is hygroscopic, sensitive to moisture, in such case, you will prefer Avicel pH 103. Accordingly, there are different grades available. These are different brand names as well, and the specifications are provided in this slide. Next is calcium phosphate dibasic. Calcium phosphate dibasic is non-hygroscopic, water insoluble, and directly compressible. Now, main problem with the dibasic calcium phosphate is it is abrasive in nature, and on repeated use, it may lead to wearing and tearing of the punches, as it is abrasive in nature. If we are not using proper lubricants, if your punches and dies are not properly lubricated, it may lead to development of scratches and wearing on the punches and dies. So that is main problem with the dibasic calcium phosphate. Another problem with the dibasic calcium phosphate is it is alkaline in nature, and hence it is incompatible with the alkali sensitive medicines. Those API which are sensitive to alkali, it is incompatible with them. It cannot be incorporated in the tablets of tetracyclines. As we know, there is a common incompatibility of calcium with the tetracyclines, and it forms a complex with the calcium compounds, and that's why it cannot be incorporated with the tetracyclines as well. So it is available under the brand names like ATEB, Dicafos, M-Compress, Fugicalin, etc. Mannitol. Mannitol is D-mannitol, that is a dextroisomer. Mannitol is commonly preferred for chewable tablets, owing to its advantage that it is having negative heat of dissolution. When it dissolves, it absorbs the heat from the surrounding environment, and that's why it provides cooling sensation, and that is why it is used in chewable tablets. Mannitol is again a sugar, a pentose sugar, and it is white odorless crystalline powder. It is directly compressible, water soluble, hygroscopic, hydrophilic in nature. and common ingredient of chewable tablets. It is available under the brand names like Improve and Perlitol. Perlitol is a common brand name. Uh, Perlitol 300 DC. It is having maximum 0.1% of particles greater than 500 nanometers and minimum 90% of particles greater than 200 nanometer in size. Perlitol 400 DC. The DC grade indicates directly compressible. Okay, the DC that indicates directly compressible. It is having maximum 20% of particles greater than 500 nanometers and minimum 85% are greater than 100 nanometers and so on. So the Politol is the most common brand name and it does not undergo a modified form such as based on the particle size. Okay. Mannitol does not undergo Maillard reaction, though it's a sugar. Lactose is also sugar, but it undergoes Maillard reaction. Mannitol doesn't undergo Maillard reaction, and that is why it can be used when lactose cannot be used. Mannitol was found to reduce the oral bioavailability of cimetidine compared to sucrose. So it has an incompatibility with cimetidine. Then binders and adhesives. Normally, binders can be incorporated in tablet in three different ways. First is dry binder before dry granulation. Second is dry binder before wet granulation. And third one as a solution binder. When we are going for wet granulation, we can incorporate the binder in two different manners. First, as a dry binder before wet granulation. So in that manner, we are incorporating binder with all the ingredients. We are mixing it with all the ingredients, and then we spray the granulating agent. The granulating agent will activate the binders and lead to preparation of granules. Or we can incorporate as a solution binder, in which we are dissolving a binder in the granulating agent itself, and then we spray the granulating agent over the mixture of all the ingredients, API, diluents, disintegrants, etc. And we prepare the granules. While in case of dry granulation or direct compression, we use only as a dry binder. So we mix the binder with all the ingredients and go for compression or go for slugging or chilchonation for preparing the dry granules if you are going for dry granulation. Now, commonly used binders are starch paste, acacia, HPMC, PVP, gelatin. They can be used as a binder. Out of this, HPMC and PVP, polyvinyl phenolidone, that can be incorporated as a dry binder. PVP is available under brand name of Polydone. Okay? Polydone. Now, next is disintegrants. The function of disintegrants is to break the tablets when we ingest the tablet. The disintegration is required to enhance the release of drug from the tablets. As you can see over here, when the tablet is intake, only the drug which is present on the surface is exposed to the resolution medium, and that's why there is minimal dissolution of the drug. When it disintegrates, it is broken down to granules. Surface area increases little bit, and it increases the dissolution rate. Further, the deaggregation is required. That is, the granules further break to fine particles. That is called deaggregation. And surface area increases to the max. So maximum dissolution will be observed when the deaggregation takes place. So dissolution rate increases as the tablet breaks down, and it enhances the bioavailability in turn. Now, for both disintegration and deaggregation, we require disintegrants. And hence, it's a common practice to incorporate disintegrants in two parts, two portions. First, as an intragranular agent, and second, as an extragranular agent. In intragranular, that is, while preparing the granules, we are mixing approximately half the disintegrant, half quantity of the disintegrant, while preparing the granules, and half the quantity is incorporated after preparing the granules, immediately before compression. So, extragranular portion includes extragranular part of disintegrant, lubricant, gradient, and antiadherent. These are the ingredients which are always incorporated after granulation, while half of the portion is incorporated as intragranular for disintegrant only. Lubricant, gradient, and antiadherent are always added after granulation if we are going for granulation. So, the intragranular portion will lead to deaggregation, and Extragranular portion will lead to disintegration. Some disintegrants like starch, they lose some of their activity when they are wetted with water. And that is why it is must for starch to be incorporated in two portions. For rest of the ingredients, if we incorporate all the disintegrants as intragranular, then also it will not cause a major issue. But for starch, we must incorporate in both the portions. The mechanism of disintegration. There are mainly four mechanisms proposed for disintegration. First one is wicking, swelling, gas generation, and enzyme action. Let us discuss each in detail. First one is wicking. As the name says, wick, the literal meaning of wick is to absorb the water from by capillary action. So all wicking type of disintegrants, they carry the dissolution fluid from the surrounding environment to the entire bulk of tablet. They distribute the dissolution fluid to entire bulk of tablet, which makes the tablet weak. Okay, this is wick, W-I-C-K, but it will make the tablet weak, W-E-A-K, and thereby it breaks the tablet. So this mechanism is observed with starch, which is most commonly used disintegrant. Now the starch is required to be used at the concentration of up to 5 to 10%. Pardon? ના. So starch નું swelling છે that એટલું બધું નથી. Starch acting on wicking mechanism. Okay. That may be because of reduction in the size. The starch which you are using, when it is compressed more time, it increases surface area. Compressed થશે એટલે બરોબર એના કારણે થાય કે wicking action વધતું હોય. બાકી normally in literature it is reported as wicking disintegrant. So it is in literature it is found that it is acting on by wicking mechanism. It pulls the water, it distributes the water throughout the tablet bulk, and it breaks the tablet. So starch is normally used in the concentration range of 5 to 10%. If we are using 10%, 5% is to be incorporated intragranular, 5% is to be incorporated extragranular. Another example of wicking disintegrant is crosspovidone. Crosspovidone is nothing but cross-linked polyvinyl pyrrolidone or cross-linked PVP. PVP itself is used as a binder. Cross-linked PVP is used as a disintegrant. Starch paste is used as a binder. Starch itself is used as a disintegrant. Crosspovidone is available under the brand name of Polidone CL. Polidone CL. Okay. It is normally used in the concentration range of 2 to 5%. It is considered as a super disintegrant. There are some disintegrants which are considered as a super disintegrants because they disintegrate the tablet at a low concentration within a short span, and that's why they are called super disintegrant. Crosspovidone is the only wicking type of super disintegrant. It is the only disintegrant which acts by wicking mechanism. The brand names available are Polidone CL, Polidone CL-M, and Polyplasdone XL. Next is swelling mechanism. There are some agents which swell up to 200 times of their original volume, and thereby when they absorb the dissolution fluid, they swell. And because of that swelling, they create pressure on the tablet walls, and that's why they break the tablet into granules and further deaggregate the tablets. The agents which are working on the swelling mechanism are sodium starch glycolate (SSG) and cross carbamylose sodium, cross-linked carboxymethyl cellulose or cross carbamylose sodium. Both are swelling type of disintegrants, and they are also coming under the category of super disintegrants. They are active at the concentration range of 2 to 8%, and cross carbamylose sodium is 0.5 to 5%. The sodium starch glycolate is available under the brand name of Explozole, Explotab, Glycolyze, Primogel, etc. While cross carbamylose sodium, that is CCS, is available under the brand names of Ecdisol, Explocel, Primulose, Solutab, Vivasol, etc. LHPC, that is low substituted hydroxypropyl cellulose, can also be used as a swelling type of disintegrant, and normally it is used in the concentration range of 2 to 5% only. Next mechanism is gas generation. There are some agents like sodium bicarbonate or calcium carbonate. When they come in contact with the gastric acid, they uh, form the effervescence of carbon dioxide. And this effervescence will break the tablet, will help in breaking the tablet. So when we incorporate sodium bicarbonate or calcium carbonate in a tablet, the tablet will break only in presence of acid. If the tablet is to be ingested, then there is no need to incorporate external acids. But if the tablet is dispersible type, that is, it is dispersed in water prior to ingestion, then we need to incorporate some acids. Commonly, we are incorporating citric acid and tartaric acid to produce, to prepare the effervescent granules. And that effervescent granules are then compressed to prepare effervescent tablet. So this mechanism is not commonly used for ingestible tablets. It is common for dispersible tablets. Next is enzyme action. There are some binders like gelatin, which are digested by the gastric enzymes, particularly in the colon. So when we are using the binders like gelatin, when the tablet reaches to the stomach, the enzymes which are present in the stomach will digest the binder. And once the binders are digested, the tablet will disintegrate. So this approach was common for targeting the colon. Gelatin has been explored to a great, sorry, not gelatin, my mistake, guar gum. Guar gum has been explored a lot as a colon targeting material because it is not soluble throughout the GIT till it reaches, the tablet reaches the colon. The enzymes which digest guar gum are present in colon. So they will digest guar gum and release the medicament. So this has been explored for delivering the sulfasalazine and 5-amino salicylic acid for Crohn's disease or colonic cancer. Ah, can it? ના ઇરોડ થશે ડિઝોલ્વ એટલે એ ઇરોડ થશે એની અંદર જે આપણે પ્લાસ્ટિસાઇઝર્સ યુઝ કર્યા છે એ ડિઝોલ્વ થઈ અને એને પેલું કરશે હા બ્રેક કરશે રપ્ચર કરશે એકલા જિલેટિનની હશે તો વાંધો આવશે પ્રોબ્લેમ થશે અને જિલેટિનના મોટો પ્રોબ્લેમ એ છે કે ડિલેડ આ ગુવાર ગમ માટે છે જિલેટિન નથી હા વન મિનિટ અહીંયા આઈ થિંક ગુવારગમ આવવું જોઈએ દેટ્સ આઈ નીડ ટુ કરેક્ટ આઈ થિંક બરોબર જિલેટિનમાં પણ મોટા ભાગે એ સ્ટમકમાં એ ઇરોડ થઈ જશે બરોબર પણ ડિઝોલ્વ નહીં થઈ શકે નેક્સ્ટ ઇઝ કોટિંગ કરી શકાય કાં તો મેટ્રિક્સે બનાવી શકાય કોટિંગ કરવું થોડુંક ડિફિકલ્ટ છે ગુવારગમનું કારણ કે એ એકદમ ટેકી મટીરિયલ છે એટલે મોટા ભાગે અત્યાર સુધી જેટલું એક્સપ્લોર થયું છે એ એઝ અ મેટ્રિક્સ જ એક્સપ્લોર થયું છે મેટ્રિક્સ બનાવ્યા પછી એની ઉપર પોલિમરી કોટિંગ કરેલા છે લાઈક યુડ્રાજિટ S100 કે યુડ્રાજિટ L100 માં next is glidants now glidants lubricants and antiadherents there are three categories of ingredients which are having nearly similar actions with a thin boundary between them so the function of the glidants is to improve the flow of granules from hopper to the dye cavity. Normally, we are using talc and magnesium stearate as a glidant. Magnesium stearate in the concentration range of 0.1 to 2% and talc in concentration range of 1 to 2% is commonly used as a glidant. Zinc stearate, stearic acid and colloidal silica are other examples. They improve the flow of granules from the hopper to dye cavity. Next is lubricants or lubricating agents. The function of lubricating agents or lubricants is to reduce, to decrease the friction between the tablet surface and the dye cavity. If you are not properly lubricating your granules, then it will create problem while ejecting the tablet. And sometimes it may lead to broken edges of the tablet. So to avoid that, we need to incorporate lubricants. Commonly, we are using talc, magnesium stearate, stearic acid, then hydrogenated vegetable oils, zinc stearate, SLS as a lubricant. Now, out of all this, SLS is water soluble lubricant. So when we want to prepare soluble tablets, then we can use SLS as a lubricating agent. If we are preparing normal tablets, then we can use any of them. But When we are preparing soluble tablets, SLS is commonly used as a lubricant because it is water soluble. Rest all are water insoluble. Now, while using lubricants, you need to take care that lubricants should not be over blended. This is the reason why we are incorporating lubricants at the end only. If we overblend the lubricants, they will bind or adhere firmly with the granule surface. If we incorporate higher amount of the lubricants, then also they will make a bilayer or tri-layer of the lubricating agent around the granules, and that will make the surface hydrophobic. Because of this hydrophobicity, the tablets may fail in the disintegration. Sometimes it may fail in the disintegration. So, over lubrication or over blending with the lubrication will lead to delayed disintegration because all the lubricants except SLS are hydrophobic in nature, and that's why we need to take care of that. Next is anti-adherence. When we are preparing the tablets, and the tablets contain some materials, some active ingredients which are sticky in nature, or granules are not properly dried, there are chances of picking and sticking. Picking is a phenomena when tablet mass is picked by upper or lower punch, and sticking is the adherence or sticking of the tablets with tablet walls. To minimize that, we need to incorporate anti-adherence. Most commonly, we are using colloidal silica as an anti-adherent that is used in the concentration range of 0.1 to 1%. The colloidal silica is available under different brand names like Cabosil, Aerosil, etc. Sometimes MCC can also be used as an anti-adherent at the concentration range of 5 to 20%. The mechanism for MCC is it is hygroscopic in nature, so it will absorb the moisture from the surrounding environment, making the mass free, that is free from moisture, or it will make the mass somewhat dry, and that's why it will enhance the ejection of the tablet. Next, these are the miscellaneous adjuvants like colorants, which commonly we are using is FDA approved dyes. Most commonly, we are using sunset yellow, Tatrazine, Sudan 123, then malachite green, etc. They can be used as a coloring agent. Flavoring agents. Normally, in tablets to be ingested, we are not using any flavoring agents. But the orodispersible tablets, or mouth dissolving tablets, or chewable tablets, they should have some flavoring agents for increase the palatability or increase the patient compliance. So commonly, we can use any FDA approved flavoring agents for preparing the tablets. Next is anti-capping agents. When we are preparing the tablets of a ingredient or API which is having poor compressibility, there are chances of capping. Capping is removal of upper or lower part, lower crown of the tablet. Now, in order to prevent capping, we need to incorporate some agents which will increase the binding within the tablet. And commonly, we are using sucrose as a anti-capping agent. Capping is more common with charcoal tablets. When we are preparing charcoal tablets, it's very difficult to compress the charcoal because it is having poor compressibility and highly friable material. And that is why in charcoal tablets, we are incorporating sucrose as an anti-capping agent. Now we'll discuss some co-process excipients. Really, co-process excipients are the excipients which contain more than one ingredients which are processed together to enhance the functionality. For an example, if a mixture or if a single ingredient serves as a disintegrant, as a binder, and as a diluent, it will be easier for a manufacturer to manufacture the tablets with a swift processing because they only need to incorporate the API, lubricate it, and compress it. No any other processing or mixing steps are involved, and that is why co-process excipients are developed by number of developers, number of industries. This is a list of some of the co-process excipients. In recent GPET exam also, it was asked about co-process excipient. That is Ludipress. Okay, Ludipress. It's a mixture of lactose, Polydone 30, and Polydone CL. Polydone 30 is povidone, PVP K30, povidone 30, and Polydone CL is cross-linked povidone or cross-povidone. Here, lactose is used as a diluent, Polydone 30 is used as a binder, and Polydone CL is used as a disintegrant. So it is a mixture of a binder, a disintegrant, and a diluent. It's a co-process excipient. It is manufactured by BASF, and it's a having added advantage of low degree of hygroscopicity, good flowability, tablet hardness independent of machine speed. Next is selectose. As the name says, it's a mixture of cellulose and lactose. So it contains 25% lactose, 75%, and 25% of cellulose. Then Diptac. It's a mixture of sucrose and 3% dextrin. Prosol. It's a mixture of MCC and silicon dioxide. Avicel CE15. It's a mixture of MCC and guargum. It is used for colon targeting. It can be used for colon targeting. Then Formex, microcellac. Microcellac is a mixture of MCC and lactose. Selectose is a mixture of lactose and cellulose. This is a mixture of microcrystalline cellulose and lactose. That's the main difference between these two. Then Pharmatose, DCL40 and Starlet. These are other examples of co-processed excipients. Now, manufacturing of tablets. Tablets can be manufactured by different methods: direct air compression, wet granulation, and dry granulation. These are most common examples. Last two, that is steam activated granulation and melt granulation, they are very uncommon, but still can be used for preparing some tablets. This melt granulation is used for preparing the effervescent tablets, because in effervescent granules we are having sodium bicarbonate, citric acid, and tartaric acid. They are sensitive to moisture. If water is used as a granulating agent, then it will lead to effervescence. And in order to prevent that, we are using the water of crystallization of the tartaric acid. We heat it, the water will be released, and it will lead to the formation of the granules. Now, this is selection process, selection flow chart of manufacturing process. Which process should you select? If your API is having good flow and compressibility, if answer to both this question is yes, you can go for direct compression. If your API is having good flow and good compressibility, we can go for direct compression. There is no need to go for granulation. If you go for direct compression, it will make the process cheaper, because number of steps of granulation, drying are omitted. So it will save the time as well as energy, and that's why the process of manufacturing will be cheaper. If any of the question is not yes, if flow is poor, next question should be, can it be improved by using glidants? Though flow is poor, but if we can improve it by incorporating glidants, if yes, we can go for direct compression. If the compressibility is poor, can it be improved by using diluents? Sometimes your drug is not having proper compressibility. It's poor, having poor compressibility. But the dose of active ingredient is 50 milligrams or 100 milligrams. And by incorporating another 50 or 100 milligrams of diluent, we can improve the compressibility. If we incorporate the diluent like MCC or DCP, we can improve the compressibility. If yes, we can go for direct compression. If no, then we need to go for granulation. Now, is your API moisture sensitive? If yes, we cannot go for wet granulation. We need to go for dry granulation. If your API is not moisture sensitive, it is not harmed by moisture, we can go for wet granulation. Out of all these three techniques, the direct compression is the fastest one, cheapest one, while dry granulation is the most tedious one. All the methods are having their own advantages and limitations. Now, out of this all, wet granulation is most commonly used method of preparing tablets. Wet granulation is having number of advantages. It is producing the tablets with uniform mass, with better crushing strength, better hardness, and better flow of granules, because the granules are prepared by wet granulation. They are having good flow, while direct compression is a time saving process, cheaper process with respect to energy and time. This is a scheme for manufacturing process. Again, here The green dotted lines show the steps involved in the dry granulation, the purple with the wet granulation, the blue one with the direct compression, and the orange one are common steps which are involved in all the processing. So in a single chart, you can find all. So API plus excipients, they are mixed together. It is required for all. Then co-milling, it is optional. Sometimes we need to reduce the size of one or more ingredients. Sometimes they are milled together, but it is optional step. Then, if you are going for dry granulation, you need to go for dry granulation. You can go for the roller compaction and then milling and then compression. If we are going for wet granulation, we go for granulation, drying, milling, and compression. If we go for direct compression, we can switch from mixing to directly compression. Rest steps are common. So direct compression is a fastest and cheapest process. It is most preferable for high-speed manufacturing and continuous processing. As we know that the pharma industry is now switching towards the continuous manufacturing, and in March 2023, US FDA has published ICH guidelines pertaining to the continuous manufacturing. So, till date, approximately 7 to 8 products already have been approved by US FDA, which are produced by continuous manufacturing. So, if we are going for direct compression, it's a better alternative for the continuous manufacturing. The steps involved are sizing. It is optional. Nowadays, all the industries are procuring the material in a particular size range only. All the suppliers are providing the material in a particular size range only. And that is why there is no need to go for sizing, mixing and compression. So only two steps are required for the industry: mix all the ingredients and compress it. It's a easy, fast and cheap process. Dry granulation, it is required when your active ingredient is moisture sensitive. At the same time, it is having either poor flow or poor compressibility or both. You cannot go for direct compression, and that's why you must go for granulation. As your API is moisture sensitive, you cannot go for wet granulation, and that is why you must go for dry granulation. Now, there are two options available in the dry granulation. First is slugging, and second is roller compaction. Let us discuss slugging first. Slug is nothing but a large size tablet. Initially, we mix all the ingredients and we compress it to produce a large size tablet. Then we break the tablet to produce the granules. We size the granules and we go for compression. We lubricate and go for compression. Okay. Now, sometimes the question may arise that if we can produce larger tablets, why can't we prepare the tablets directly? If we can prepare this tablet direct by compressing, why can't we prepare the original tablet directly? The answer to this question is, when we prepare slugs, we are not much interested in the weight variation. We are not much interested in the content of the active ingredient. So, when we prepare slug, they are subsequently broken to granules. The granules which we are using are sized. That's why they are having uniform size, and hence they are having uniform flow. At the same time, we are incorporating binders, and they will increase the binding strength, that is compressibility. And hence, the granules which are prepared after dry granulation are having both the advantage, good flow and good compressibility. If we are going for directly preparing the tablets which we get may not have uniform weight and uniform active ingredient content. And hence, we need to go for granulation. Next is roller compaction. It's also known as chilsonator. Roller compactor is also known as chilsonator. As the name says, here the mass is compacted or compressed between two rollers. This is a feed screw which feeds the mass. These are two rollers which are moving in opposite direction to each other. When our mass come in contact with these rollers, in between the rollers, it is compressed, and a sheet of the mass is formed. The sheet is then broken down with a hammer mill. This is the pre-breaking, primary breaking. Then it will move to the next chamber in which there will be actual granulation, and at the bottom a screen is fitted. The granules which pass through the screen are further screened in three different sizes. Here there are two slanting sieves. These are slanting sieves. So the granules which are oversized, say for a tablet manufacturing, we require the granules of a size 2040. That is, they must pass through 20 mesh sieve and they must be retained on 40 mesh sieve. Depending on the tablets which we want to prepare, the size of the tablets which we want to prepare, we select granule size. For smaller size tablets, we prefer smaller granules. For larger size tablets, we prefer larger granules. So if our tablet weight is 500 milligrams or more, we go for 1020 granules. If the weight is less than 300 milligrams or around 300 milligrams, we go for 2040 granules. So this upper screen will reject the oversized granules. The actual size granules will pass through them. The fines which are having size lower than the lower cutoff. Say, for an example, if you are preparing 2040, the upper screen is 20 mesh, lower screen is 40 mesh. So the granules which are larger than 20 mesh will be rejected. Then they will pass and they are exposed to the next sieve. If they are smaller than 20 mesh, they will pass through the screen. If they are larger, they are collected as a product. Now, the fines which we have collected are also important, because while preparing the tablets, normally we are incorporating 15 to 25% of the fines in order to make the granules spherical. In order to increase the compressibility and flowability, we have to incorporate approximately 10 to 25% of fines. So we will take some of the fines, and the rest of the fines and overs are recycled. They are fed again to the roller compaction. So this is the main advantage of the roller compaction. If we are going for wet granulation, it is difficult to recycle the overages, the oversized granules and fines. In case of roller compaction, they can be easily recycled because they are not coming in contact with any granulating agent. They are only in a dry form, and that's why they can be compressed again and they can be converted to original size granules. Next is wet granulation. It is the most commonly used technique of preparing the granules. Wet granulation is having number of advantages. First is it is having proper distribution of the binders. If we are using dry granulation or direct compression, we cannot ascertain that the binder has distributed properly or not because it's in a dry form. While when it is in wet form, we can check it whether it has distributed uniformly or not. When the mass, if it is found to be dry at some place, we can incorporate extra binder over there and we can make it uniform. So with wet granulation, it is easier. Another thing is when we are going for wet granulation and when we subsequently dry the granules, there is a phenomena that is called solvent migration. As we are drying the granules, initially the solvent from the surface will evaporate. Then the solvent from the bulk will diffuse through the pore and it will travel to the surface. When the solvent from the bulk travels to the surface, it carries along with it some amount of the binder, and that will make the surface of the granule binder rich. It is having more amount of binder. Now, granule itself is prepared by wet processing, and that is why it is having good binding. But when two granules are compressed together, when they join together, they should have higher amount of binder, and that is possible or that is available with the wet granulation. So this binder rich surface will help in preparing the tablets with good compression strength, good crushing strength. These are the steps involved in the wet granulation process. The equipments which are used for wet granulation, commonly used equipment is RMG, rapid mixer granulator. This rapid mixer granulator is having two type of blades. This is a rotor blade and this is a chopper blade. The function of the rotor blade is to rotate the mass, while the function of the chopper blade is chop the mass. The chopper blade is mounted at one place and the rotor blade will rotate all the mass around the within the RMG. Normally, The spray gun is placed at the top, which will spray the granulating agent. Once the mass is becoming wet, it will become denser, and it will experience more centrifugal force. As it experiences more centrifugal force, it will be thrown towards the corners or sides of the vessel, and they will come in contact with the chopper blade. So chopper blade will break it. This continues till we attain granules of a proper size. Now, the end point of any granulation process is normally measured by the energy consumption. As we know that it is easy to mix the dry material. As the material becomes more and more wet, it becomes difficult, more and more difficult for us to mix it up to certain point. Once the amount of liquid increases beyond a certain limit, further it becomes easier to mix them. So the curve of the energy consumption is like a bell. It's a bell-shaped curve. So we can easily detect the end point by energy consumption. If the mass is damp enough, it will consume maximum energy because damp mass is very, very difficult to mix, difficult to rotate, and that's why we can easily detect the end point. Nowadays, the IR probes are also available, which will detect the moisture content in the granules, and we can stop the process. But uh, the energy consumption can also be used as a parameter. This is a flow sheet of the tablet manufacturing. The drug, which is ground, it is blended, liquids are added to prepare agglomerates, then it is passed through screen to prepare the granules, then they are dried, they are screened again. During drying, there are sometimes chances of shrinkage of the granules. When we are passing through sieve, the size is larger. After evaporating the solvent, size decreases to some extent, and that's why we are going for screening again. Here, the screening is done for two things. We are rejecting the above oversized because sometimes there are formation of aggregates, and they will have size more than that of the required size. Sometimes they shrink to form the fines. So we are rejecting fines as well as oversized granules. We go for screening. Again, we blend with the lubricant, glidant, anti-adherent, and extra granular portion of the disintegrant. In this blending, we are incorporating API, diluent, and disintegrant. Only three ingredients are commonly incorporated over here. And the binder, if it is used as a dry binder. If it is used as a solution binder, it is incorporated as a solution. And then we compress to prepare tablet. Now, all-in-one granulation process. Currently, the industries are working with the all-in-one granulation process. Most common example of that is the fluidized bed systems. In fluidized bed system, we can carry out mixing, granulation, drying, all in one, all at a single stage. So we can mix the ingredients, we can granulate it, and we can dry it. So that is called all-in-one granulation. So in fluid bed granulator, a pre-blending of the formulation can take place with the API, diluents, disintegrants, and binders. The granulating mixture can be sprayed to prepare the granules, and that granules can be dried within a single chamber. This is a cross section of a fluidized bed system in which at the bottom there are perforations through which we can flow the air. The air will fluidize the material. Now, the air will have different qualities at different stages. If we are using the air for mixing or granulation, it is a dry air, normal air, not hot air. If we are using for drying, it is dry hot air. So for different stages, we are using different air. At the same time, we are using different flow rate of air as well. So if you are using for going for mixing, the airflow rate is somewhat lower. If you are using for going for granulation, the airflow rate required should be increased because the mass becomes damp, and as it becomes damp, its density increases and more force is required to make it fluid. While drying also, we are increasing the flow rate and we are increasing the temperature of the air as well. So all the processes take place in the same chamber. This is continuous fluid bed granulator. As I mentioned earlier, WHO, USFDA has published the final guidelines ICH Q13 guidelines, which are related to continuous manufacturing. Now, more and more industries will join this trend. They will produce more and more products by continuous manufacturing. And hence, this is an example of continuous fluid bed granulator, in which from one end we can feed the mass, and from next end we can collect the granules continuously. Okay, so there are different stages. If you look at the diagram, it shows this is primary spray, secondary spray, tertiary spray, and this is drying stage. So in the same chamber, we are having four different air inlets. As it is apparent from here, there are four different air inlet zones in a same chamber. In one, the air will be dry, normal temperature. It is only fluidizing the material. In second, it will have somewhat more higher temperature and higher flow rate because it has to fluidize the wet granules of a larger size. Here, in the first zone, it's a powder. In second zone, somewhat larger granules. Here, the largest granules. So, flow rate further increases. In the last chamber, we need to dry the granules. So, we are feeding the hot air with a larger flow rate. So that will dry the granules, and the dried granules are collected. So it's a continuous fluidized bed drying. Next is microwave processing. Industries are now also preferring the microwave processing for preparing the granules as well, in which we can use the binders which can melt by heat, and they can provide the binding action. So this is also called microwave assisted granulation. Microwave assisted granulation. Microwave provides the heat for melting the granules, and the granules binder, and the granules will be formed. This is an image of microwave processor. Now, tablet press. Mainly, we are using two type of tablet press. One, that is single punch tablet press or tablet machine. Second is rotary tablet machine. Under rotary tablet machine, there is one more type available, that is called double rotary tablet machine as well. But that is a part of rotary tablet machine only. So, previously, at laboratory scale, we were using single punch tablet machines. Nowadays, that have also become obsolete. And at laboratory scale also, we are using rotary tablet machines, but they are having less number of punches, approximately 10 to 16 stations. While at a large scale, in industrial scale, we are using up to 27 station tablet machines, and that are also double rotary. Now, first, the parts of the tablet machine, punch and die. They are most crucial parts of the tablet machine, punch and die. In a rotary tablet machine, we are having a set of die and punch for each station. Say, we say the 10 station rotary tablet machine. That indicates it is having 10 sets of dies and punches. 27 station rotary tablet machine, it is having 27 sets of dies and punches. It includes one upper punch, one lower punch, and one die cavity. Now, all these three are moving together in a rotary tablet machine. So, a particular die will only be in contact with that particular upper punch and that particular lower punch. They will never be separated. Okay. So, this is your upper punch, this is your lower punch, and this is the cross section of die cavity. If we want to identify the upper punch and lower punch, or we want to differentiate them, normally the length of this portion is more in case of lower punch, while in case of upper punch it is less, because upper punch has only to be penetrated to half the depth of the die cavity, while the lower punch is used for adjusting the volume, ejecting the tablet, and compression. Lower punch has three functions in a rotary tablet machine: weight adjustment, ejection, and compression, while upper punch only helps in the compression. These are different shapes of punches available. This is shallow punch, this is concave punch, deep concave punch, rounded, and completely rounded. Depending on the requirement, we can use any punch. If our tablets are to be coated subsequently, we need to use the concave punches or deep concave punches, because the rounded edges of the tablets will facilitate the cascading of the tablets in a coater. But if the tablets are not coated subsequently, they are normally prepared with flat face punch, that is flat tablets. The main problem with the concave or deep concave punches is the edges. They are very delicate and they may sometimes bend during the faster processing if the punches are not rising properly to the surface of the die table, and that causes a problem that will lead to capping and sometimes lamination. So normally we avoid the concave or deep concave punches unless they are required. Now, tooling. Mainly there are two types of tablet tooling available: B tooling and D tooling. The difference between B tooling and D tooling is the head diameter and barrel diameter, the diameter of the punch head and the diameter of the punch barrel. That makes a difference. Now, in industries, when we go for higher compression forces, we require larger barrel diameter so that it can withstand higher pressure. And in laboratory scale, we require lesser compression force, and that's why we use lesser barrel diameter. So B tooling is preferred in the laboratory setup, and industrial setup, particularly for faster processing, we prefer D tooling. So the B type configuration has a normal punch barrel diameter of 0.75 inches, that is 19 mm. The B type can be used with two types of die, or can be said to have two different die size. The B dies with a diameter of 1.1875 inch, that is 30.16 mm, which are suitable for all tablet size up to maximum for B punch. And the smaller, that is BB dies, that has diameter of 0.974 inch, that is 24 mm, and this type is suitable for tablet up to 9 mm diameter or 11 mm to the max. The D type has larger nominal barrel diameter of 1 inch, that is 25.4 mm, as compared to 0.75 inch over here, and die diameter of 1.5 inch. Over here, maximum die diameter is 1.18, that is 30 mm. Here it is 38 mm, and thus it is suitable for tablets with a maximum diameter of or maximum length of 25.4 mm. When we are preparing elongated tablets, we can use D tooling. The tablet press is designed to be used either with B tooling or D tooling because the punch head is also having the same diameter as that of the punch barrel body, and the turret which we are using, or track which we are using, it will only hold or guide that size diameter, and hence we can use either B tooling or D tooling in a particular machine. We cannot use both together in a single machine. So the machines that are designed to B type of tooling, they exert maximum compression force of 6.5 tons. In the machines which are using D type, they exert maximum pressure of 10 tons. There are some special machines that are designed with the intention of exerting higher compression forces. If your material is not properly compressible, we can increase the compression pressure as well. These are the dimensions, complete dimensions of B tooling and D tooling. So this is called punch head. The diameter, this is B tooling, this is D tooling. Length is nearly similar to both, okay, for upper punch and for lower punch. This portion that is shorter in upper punch, longer in the lower punch. Diameter differs in both B tooling and D tooling, as we already discussed. Okay, these are the die cavities. Now, single punch tablet machine, as the name says, it is only having one set of die and punches. Here, in a single punch tablet machine, the lower punch regulates the fill volume. Compression force is least affected by the lower punch, and it ejects the tablet, while the compression force is adjusted by the upper punch only. Compression force is adjusted by the upper punch only in a single punch tablet machine. So in single punch tablet machine, one tablet will be produced per cycle. In a rotary tablet machine, the Number of tablets produced per cycle will depend on the number of stations. In a 10 station tablet machine, 10 tablets are produced in cycle. In 27 station double rotary tablet machine, 54 tablets are produced per cycle. But in a single punch tablet machine, one tablet is formed per cycle. This is a single punch tablet machine. This is hopper. This is compression wheel. It can be operated manually or using a machine. Here, there is a shaft which will help in compression. This is the shaft which regulates the lower punch. And there is one hopper shoe. I'll show you, I think, animation that will facilitate. Yeah. This is the animation that shows the tablet compression in a single punch tablet machine. Now here, the movement of the punches is reciprocating movement. They are only moving up and down. In rotary tablet machine, they are having two type of movement: circular movement as well as reciprocating up-down movement. Over here, there is only one type of movement: up and down, up and down. Now, this is called hopper shoe. If it it is having two functions: filling the die cavity and ejection. Filling the die cavity and ejecting the tablet. Lower punch by volume adjustment and ejection. Look at the compression cycle closely. During compression, the lower punch is stationary. It is not moving. In a rotary tablet machine, the lower punch will also move during compression. In single punch tablet machine, the lower punch will not move during compression. So compression force is only adjusted by the upper punch. So it is having two tasks: volume adjustment and ejection. Upper punch only facilitates in the compression. So this is a sequence of events. First is the die surface view. It's a top view of the die surface. The hopper shoe. It is called shoe because it is having the shape like a shoe. It travels and moves above the die cavity. So it fills the die cavity. It moves backward and compression takes place. And then the tablet is ejected. And the hopper shoe will push it to the collector. As the sequence is shown, first and second position are filling, then compression, and fourth position is ejection. The tablet, single punch tablet machine is easy to operate, small scale. At the industry level, we can, at a small scale industry or laboratory level, we can use it. It can produce up to 300 tablets per minute if we are using at a faster, using a faster machine. While in a rotary tablet machine, we can prepare millions of tablets per hour. The rotary tablet machines are equipped with multiple punches and die, which operate via continuous rotating movement of the punches and die. A single rotary press with 16 stations, that is 16 states of dies and punches, may produce up to 1150 tablets per minute. For such high-speed production, induced die feeders are used. We can to improve the flow, we are using induced die feeding. That can be induced by either rotating or vibration. There are two mechanisms possible: rotation and vibration. This is a 10 station rotary tablet machine, mini press 2. This is a cycle which is shown in a cross section for tablet manufacturing. First step is die filling. Here there is a feed frame. Through hopper, the granules enter the feed frame. The lower punch lowers, that is, it adjusts its capacity. As you look at this, there is a ramp. So lower punch is lowering, it is coming down and it is increasing the fill volume. Over here, till this point, the filling will take place. Now, there is a weight adjustment knob over here. We can increase the elevation over here, and that helps in the weight adjustment. Normally, initially the die is overfilled, and then the ramp is somewhat tilted so that the extra mass will move upward. This will help in rearrangement and proper die filling, and that is why the arrangement is done like that. So this ramp is used for weight adjustment. We can tilt it, we can increase the angle. So initially the die is overfilled, then this punch rises, which will push the mass upward and rearrange the granules, and then there will be a scraper which will scrape the granules. This is a pre-compression roller. Normally, pre-compression is done to eliminate the air which is entrapped while filling the die cavity. Air entrapment is essential because once if air is present, once we compress the granules, the air is also compressed along with the granules. Once the compression force is taken away, the compressed air will try to regain its original volume. And during this, it will break the tablet in more than one layer. That is called lamination. So to avoid lamination, pre-compression is required. And that is why this is a pre-compression roller in which we are providing lesser compression force. So the mass will be compacted, the force will be taken away, and the air will escape from the pores. Then the tablet is originally compressed, and then it is ejected. So the one end of the feed frame will help in the ejection. Once the lower punch rises, it will move the tablet to the surface, and one end of the feed frame will scrape the tablet away. The upper punch is guided by this track. At the top, there is a track which will guide the upper punch. So, during most of the time, the upper punch remains in a raised position. Only during the compression, it moves to the die cavity, it compresses and again moves back. So, when it is under the compression roller, it is entering the die cavity. In rest of the time, it is raised above by the track. This is an animation which shows the compression cycle. This is weight adjustment ramp and this is weight control unit. We can rotate this screw and move the position of this ramp. So if we raise it further, the blend will rise. This is a scraper. This will remove extra granules. This is a feeder or feed frame. These are the dies which are filled by material. This is a pre-compression roller. As if you look at this, this is called track. This will guide the upper punch. So the upper punch are only entering the die cavity during compression. For rest of the time, they are in a raised position. This is a pre-compression roller, and this is a main compression roller. Over here, there is a ejection cam. So the lower punch will rise. It will lead to the tablet to the surface of the die table, and the scraper will, that is the one end of the feed frame, will eject the tablet. The rotary tablet machine is having number of advantages. High productivity. It can output can range between 9,000 to 2,34,000 tablets per hour. And thus, it saves time and meets up the high demand. It power field cavity can be automatically managed by moving feeders. And the machine allows independent control of both weight and hardness. We can adjust both crushing strength and weight. The difference between single and double punch tablet machine is the single punch tablet machine utilize a single-sided compression, that is only upper punch. While in the rotary tablet machine, it is a double-sided compression. Both upper and lower punch are under compression roller. If you look at the image, both upper punch and lower punch are coming under compression roller. So both are taking place in compression. In single punch tablet machine, only upper punch is under compression roller. So that is only adjusting the compression force. The single punch tablet press compression cycle do not have a dwell time. Yeah, dwell time is an important parameter that will decide the stability of the tablet actually after preparing the tablet. There are some materials which are elastic in nature and they will try to regain their original size and shape. When they are compressed, they get compressed. Once we remove the compression force, they will try to regain their original weight and volume and shape, and thereby they lead to lamination and capping. So that deformation is required to be completed before during compression. For this elastic deformation, we need to increase the dwell time. So dwell time is the actual time for which the upper punch remains in the die cavity. That is, it is actually compressing the tablet. Now, the dwell time can be increased by two mechanisms. First is by slowing the speed. And second is by using the compression rollers of larger diameter. If you look at the animation over here, the compression roller which we are using for main compression is of larger diameter. So the larger diameter is having more flat portion, and thereby it will force the punch to remain inside the die cavity for a long time. If it is having smaller diameter, the curvature will be sharp. So the punch will remain for a lesser time or exert the compression force for a lesser time. As the curvature decreases, diameter increases, curvature decreases, and thereby it will keep the upper and lower punch in a compressed position for a long time. So it will increase the dwell time, and thereby it will lead to deformation. And hence, the materials like paracetamol or metformin will not try to regain their original volume, and thereby they are having better strength or stability after preparing the tablets. Then double rotary tablet machines. Now, as we have studied the rotary tablet machine, they are always having the number of punches or dice set in even numbers. The rotary tablet machines are always having the die and punches in odd numbers. That is principal difference between the rotary tablet machine and a double rotary tablet machine. The common logic behind that is to distribute the forces. If we are having even number of punches, both the compression rollers are exerting the pressure at the same time on the die, and that may sometimes disturb the die or may lead to excessive pressure on the die table. So the cycle is alternate. Once one roller is pressing, another is in a relaxing position, and so on. So at same time, both rollers are not above a punch. Clear? At the same time, two punches are not under a roller in a single machine, double rotated machine. So the cycle will continue like this, and thereby forces are distributed uniformly. And that's why the rotated machine are having two hoppers, two rollers for the compression, but odd number of punches. This is there's an image of double rotary tablet machine. It's having two hoppers, two compression rollers opposite to each other. And this is a 15 station double rotary tablet machine. Oh, 45 station, sorry. 45 station rotary tablet machine. So number of punches will always be odd. Now, last part of this chapter, that is problems and remedies. When we prepare the tablets, there are some problems which arise, and we will discuss the remedies for the same. First is picking and sticking, capping and lamination, mottling, weight variation, friability, double impression, chipping, and cracking. Capping and lamination. As it's shown over here, the upper crown or sometimes the lower crown of the tablet gets separated from the main body. That is called capping. Only cap is removed, and that is what is called capping. When the tablet separates in two or more layers, it is called lamination. Okay? Now, what are the reasons for lamination? First reason is air entrapment. As I discussed earlier, if air is entrapped while preparing the tablets, once we remove the compression force, the air will try to regain its original volume, and thereby it pushes the layers apart from each other, and that leads to capping and lamination. So if it is due to air entrapment, it can be prevented by pre-compression. Next is deformational properties. Plastic deformation is more than elastic recovery. In such case, we can increase the dwell time. For increasing the dwell time, either we can slow the speed or we can reduce the final compression pressure. And we can use if we are using deep concave punches, then they may result in the capping. If we are using deep concave punches, while ejection, the speed of the machine is higher, and at the same time, lower part of the tablet remains within the die cavity. Thereby, there are chances of capping. So, we can adjust the proper settings, or we can use the flat punches. If it is not required, then we should prefer flat face punches. Then overdried granules. If your granules are overdried, if they are having moisture content less than 2%, then there are chances of capping and lamination because there won't be proper binding. Ideally, in a tablet, granules, you should have 2 to 4% of the moisture. If the moisture content is less than 2% or more than 4%, both are problematic. So if less than 2% moisture is present, it leads to capping, lamination, and friability. If moisture is more than 4%, it leads to picking, sticking. So all are problematic. So if granules are over dried, we need to maintain the moisture content. Then development of wear ring in the die cavity. Sometimes after repeated compression, a ring is generated within a die cavity, and that wear ring will lead to forced ejection. The lower punch needs to force much to the tablet for ejection. And that will lead to capping and lamination because the forces are not distributed uniformly by the lower punch, and hence the capping and lamination may be generated. So we can either change or invert the die. Inverting the die will solve a problem for some time because compression always takes place in upper one third part of the die cavity. So if you invert the die, the lower part, which was previously exposed to only lower punch, is now exposed to compression, and there won't be any issue. Then incorrect setup at the press. If you are not adjusting the lower punch properly, if your lower punch is not rising to the die surface properly, that during ejection, some part of the tablet will remain inside the die cavity. And when the tablets are scraped off, they will break. It will lead to capping and lamination. So adjusting the ejection height can minimize or prevent this problem. Next is picking and sticking. Picking is the removal of upper and lower mass from the upper and lower part of the tablet by upper or lower punch, as it is shown over here. These tablets are picked. Sticking is adhesion or sticking of the tablets to the die cavity. In such cases, the sides of the tablets will have some lines or scratches. Now, this picking and sticking are because of the engraving or embossing. Sometimes, when we are using the punches which are embossed, then the narrow areas will lead to more picking. Narrow enclosed areas will lead to more picking. So we can change the fonts. If you are using such kind of fonts, they are having least narrow areas, and that's why picking and sticking can be prevented. Next is improper lubrication. If lubrication is not proper during injection, the forces are not distributed uniformly, and thereby it will lead to layering, that is lamination in the tablets. So we can incorporate proper lubricants. Higher moisture in the granules. If the moisture content is higher, then also there are chances of picking and sticking. And hence we can dry it. Then sticky material in the formulation. If material is sticky, we can use adsorbents, which will decrease the stickiness, and we can use anti-adherents. Rough punch surface. If your punch surface is rough, then also the mass will stick. So in such case, we can go for chromium coating of the punches or replace the punches. Then low melting components in a formulation. If a formulation is having low melting component and during compression, heat is generated, the material will melt. It will make the mass sticky, and that's why mass will stick to the die cavity or will be picked by upper or lower punch. In such case, we can use either cooling mechanisms or we can slower the speed of manufacturing in order to prevent the heat generation. Next is mottling. Mottling is uneven distribution of the colors. When we are preparing the tablets which have more than one colored medicine, API, particularly for an example, multivitamins, or when we are incorporating coloring agent to mask some of the colors. In such case, there are chances of mottling, that is uneven distribution of the color. The reasons for mottling can be colored API. We can use coloring agents to mask the color of the API because the amount of API is less, and all the ingredients which we are using like diluent, binder, disintegrant, they all are colorless. So the API where it is present, it will appear like a patch, and it will create mottling. So we can use coloring agent. Next is migration of dye. As I said, with the wet granulation, the solvent migration will lead to migration of binder to the surface. Similarly, if we are using water soluble dyes, The dyes will also migrate during drying of the granules to the surface of the granule, which will make the surface with higher density of the dye. Internal part will have lesser density. When this granule is compressed, sometimes it may happen that the internal part is exposed to surface and hence the tablet will appear to be motile. In such case, we need to use water insoluble dyes and blends, which are not soluble in water. They will not migrate along with the water during drying. Weight variation. Weight variation is a problem which may be because of improper dye filling, most commonly because of improper flow. When your granules are not having proper flow, the dye will not be filled uniformly, and hence the weight will not be equal. So, if the granule size is broad, then segregation may take place. If flow is poor, dye will not be filled properly. If mixing is not proper, if higher density material and low density material are together and they're not mixed properly, then also weight variation will be there. And punch variations. Normally, nowadays, this problem don't arise. Punch variation is when all the punches are not having proper size, uniform size. At that time, some dies are not filled properly. But nowadays, the punches are manufactured on high precision machines, so all are having equal size, and that issue is not at present observed at all. Next is friability. It is a breaking of the edges of the tablet. The friability can be because of improper binding. When your binder is not proper, you need to increase the concentration of binder. It can be because of improper drying, that is over drying of the granules. If the granules are not over dried, they will have lesser moisture content, and that will lead to poor binding in the tablet. And hence, we need to uh, prevent the over drying of the granules. Then low compression pressure. If the tablets are not compressed properly, then the hardness, that is crushing strength, is less. And last one is over lubrication. If the granules are lubricated to more extent, then that will prevent the binding, because lubricants are hydrophobic in nature and they will prevent the binding between the granules, and hence friability will be higher. Next is double impression. When we are using embossed punches, okay, embossing, at that time there are chances of rotation of the punches between the pre-compression and compression, because the track is guiding the punches, and that's why the punches may sometimes rotate to some degree, and that will increase chances of double impression. So in such case, we can use punch locks. At the side of the die table, there is a lock available in which we can prevent the movement of the punches, and by using that punch locks, we can prevent the rotation of the punches. So